Hi and hello to everyone. In this video, we are going to look into the applications of Opamp. In the last video, we looked at applications like inverting amplifier, non-inverting amplifier, buffer, voltage follower, adder, and difference amplifier. In this video, we are going to look into main applications like differentiator and integrator. Okay, in differentiator, we'll be seeing the ordinary differentiator and we'll be seeing what is the drawback of ordinary differentiator. Thereby, we move into practical differentiator using Opamp. Similarly, we will look at integrator circuit and we'll look into the practical integrator circuit. For both the differentiator and integrator circuit, we will look at into the few examples. Welcome to the lecture. First, let me start with the differentiator. What is a differentiator? Differentiator will process the input. Okay, will differentiate the input signal. Okay, the output of a differentiator will be the differentiation of the input signal. Right. So this is the differentiator circuit. You have to remember this circuit. As usual, there is a feedback. Okay, from the output to the inverting terminal, and there is a capacitor connected to the inverting terminal. Other end of the capacitor is given the input signal Vin. We will take the output as V0. The non-inverting terminal is connected to ground. We know from the op-amp concept, if the plus terminal or the non-inverting terminal is grounded, the minus terminal is also at zero potential. That's why we say it is virtual ground. This is actual ground. This point is virtual ground. That is at 0 volt. Let us consider the current flowing through the capacitor is IC, the current flowing through the resistor is IR, and the current flowing into the op-amp inverting terminal is I. By applying Kirchhoff current law KCL at the node A, this is the node A. Node is nothing but the intersection point or the connecting points. At this node, we have three branches. This is branch 1, branch 2, branch 3. Okay, at node A, we are going to apply Kirchhoff's current law KCL. Incoming current is IC. This is another incoming current is IR. The incoming current at the node A is IC plus IR is equal to outgoing current is I. That is the Kirchhoff current law. Okay, Kirchhoff current law states that incoming current is equal to outgoing current. Sum of incoming current is equal to sum of outgoing current. Okay, what about IC? IC is the current flowing through the capacitor. What is IR? Current flowing through the resistor. We know the current flowing through the capacitor is given as I equal to C dV by dt. Okay, here the V is the voltage. What is the voltage across the capacitor? At one side, the potential is Vin. At the other side, it is at virtual ground, so 0 volt. Okay, so Vin minus 0 by dt. So C differentiation of Vin minus 0 by dt. Similarly, what is the current flowing through the resistor? At one side, the potential is V0. The another side, it is at virtual ground, so it is 0. So V0 minus 0 by R. Voltage by resistance is equal to 0. Okay. On simple mathematical manipulation, we will be finding out that what is V0. We need the relation between output and input. So V0 is equal to minus RC times differentiation of Vin. Okay, that's why it is called differentiator. Output is equal to differentiation of the input signal. What about RC? R and C are R is the resistor value, C is the capacitor value. These two are constant. Okay, so output is equal to some differentiation of the input signal. Such circuit is called differentiator circuit. Now, what about the minus sign? Minus sign indicates that you are connecting the input signal to the inverting terminal. That is why it is called I can say inverting differentiator. It can be also called. This minus sign is due to the input is coming to the inverting terminal. Right. Now to find the response, we are working everything in time domain. Right. See V0 of t, Vin of t. But thing is, in electronics or communication, we are interested only in the frequency domain. What is frequency domain? Because where and all we use the frequency. If you are tuning to an FM. Okay, you have a FM in your home. If you are tuning to the FM, what you will do? For some channel, we will say 110 megahertz. For some channel, we say 98.2 megahertz. Okay, that is called frequency. Based on the frequency, we can select the signal. Right. Similarly, we can convert from time domain to frequency domain. Right. So, converting from time domain to frequency domain, it gives more information. As I said, the television signal we are seeing in a TV, FM signal are all based on frequency. For a particular frequency, we can receive a particular channel, right? So we will convert the time domain to frequency domain. In time domain, if I say d by dt, that's a differentiation. I can frequency domain, I can say it as j omega. Similarly, v naught of t, I can say it as v naught of omega. So v in of t, I can say it as v in of omega. Thereby, this omega is nothing but frequency domain. Frequency domain gives more information. That's the important thing, right? Now, I can convert this expression, that is v naught of t equal to minus rc dv in of t by dt into frequency domain. So v naught of omega minus differentiation becomes j omega, minus is there, so minus j omega rc v in of omega. Okay, right. Now what is omega? Omega is nothing but the angular frequency. Angular frequency, that is your 2 pi f. 2 omega is 2 pi f. Now we will take the magnitude. What is the magnitude? Magnitude of minus j is, see, magnitude of j is 1. Minus j is also 1, right? Because j is square root of minus 1, magnitude becomes 1. Magnitude is always positive, keep in mind, right? So I can take the magnitude. So what is the magnitude? V naught of omega by V in of omega equal to omega RC. Normally we will represent the magnitude in decibel scale. This is in normal scale, V naught by V in, or I can say gain. V naught by V in is gain, output by input. In frequency domain I say gain. I can represent the gain in decibel. In decibel, what we do? 20 log base 10, right? I take 20 log, so it becomes 20 log omega RC. Similarly, since this is a complex number, right? Anything in complex number will have a magnitude and will have the phase angle. We will have the phase angle, right? Okay, what about the phase angle of J? Phase angle of J is 90. Okay, phase angle of J is 90 degree. Phase angle of minus J is minus 90 degree, right? So angle of V naught of omega is angle of V naught of omega. V in of omega I put angle, right? So difference between the output angle and input angle is equal to minus 90 degrees. So output and input is differed by the phase angle of minus 90 degree. This information is obtained only in frequency domain, right? Frequency domain gives what frequency, how the circuit is going to behave, because our IC is an analog IC. Analog IC input signal is an continuous time signal. Continuous time signal will have definitely frequency. Okay, because I can say that, see, we are talking in a mobile phone, getting the signal in particular frequency, right? Our radio is operating at particular frequency, right? We see if something like see, if people are using walkie-talkies, it is operating at particular frequency, right? We cannot interfere in those frequency. Bluetooth is operating at some frequency, right? So those frequency information can be obtained only from the frequency response. Okay. Now what we are going to do is, we are going to assume R as 1 mega ohm and C as 1 microfarad. Mega we know is 10 power 6, micro is 10 power minus 6. Particularly why I am choosing this value is because we are going to multiply R into C. Okay, R into C, 1 in 10 power 6, 1 in 10 power minus 6. So product becomes 1. Okay, R into RC product is 1, right? Now when RC product is 1, look at this, RC is 1, so 20 log omega by 10, right? And this is how we will plot the magnitude response, and we will look at this scale. This scale is in logarithmic scale. Logarithmic scale means it is increasing in the multiples of 10. Okay, like I have plotted, assumed the value 10 power 0. 10 power 0 is 1, 10 power 1, 10 square, 10 cube, 10 power 4. So equally, if you look at this range, it is incrementing by 10. And this axis is the magnitude in decibel. Okay, that is a 20 log omega RC. Right? We for this I have assumed RC, R and C values such that the product is 1. Okay, right. Now our observation is, look, when omega is increasing, RC is 1, right? When omega is 1, 20 log 1 is 0 dB. When omega is 10, 20 log 10 base 10. 10 base 10 is 1 to 20. Omega is 100, 20 log 10 square. So 2 square, 2 term 2 comes here, to 2 into 20 is 40, log 10 base 10 is 1, right? Then 20 log 10 cube is 60, 20 log 10 power 4 is 80. So we can see this is how the magnitude response will be like. So when omega is increasing, the gain increases linearly. right? Not against, I can't say it's linearly because everything is in, yeah, I can say it's linearly because we are taking the magnitude in decibel and this omega is increasing 10 times, right? But what is the, then what about the frequency? We'll look at the drawback next, right? Next we'll see the phase plot, the difference between the output and input. Output is V naught of omega, V in of omega. The difference is minus 90 degree. So minus 90 degree is a constant. Okay. What is the issue with this system? Issue with this system is at high frequency, when omega is increasing, what happens to the gain? It will keep on increasing. Also so high, so the output gets saturated. Okay, when the gain gets increased, output gets saturated, right? We know output of the op-amp is only plus V, maximum is plus V saturation, minimum is minus V saturation. When the output, when the gain is keep on increasing, output gets into the saturation region. That's the drawback, right? So how to overcome this drawback? For this, we'll go into the practical differentiator circuit. Okay, practical differentiator circuit, right? Before going to that, we'll work out a few problems. Two problems we'll work it out, right? Let me say this is the differentiator expression, ordinary differentiator expression. This is how we did. This is what we derived in the last slide. And given the R value as 1 mega ohm, C value as 1 microfarad. The question is V in is given. Find out V naught. Find V naught. Find V naught. Question is find V naught of T. That is the question, right? Okay. So what you have to do, look at this expression, R value is 1 mega ohm, C is 1 microfarad, so product is 1. So dV in by dt, differentiation. What is differentiation? Rate of change. So look at this part of the waveform. The change in amplitude is 2, change in time is 1. How to find out 2 minus 0, 1 minus 0, so change is 2. Okay, so the change is 2. Look at this part of the waveform. What is it change? It is changing from 2 to 0. So what is the change? 0 minus 2. 0 minus 2 divided by 2 minus 1. Okay, right? The change in amplitude, is what? 0 minus 2. The change in time is 2 minus 1. Okay, so it is minus 2. So this is minus 2. Minus 2. Similarly, for this part of the waveform, the change is 2 minus 0, upper limit minus lower limit. Similarly, for the time 3 minus 2, 1. So the change is 2. Okay, so this is what we get once we differentiate this waveform, that is dV in by dt. But the question is minus RC dV in by dt. RC is 1, so we have a minus sign. Minus sign just says that just you invert. So wherever you have plus 2, we will get minus 2. Wherever we have minus 2, we will get plus 2. So positive will come to the negative side. Negative part is between 1 and 2 goes to the positive side. So this is, so if we give V in, this input to our differentiator circuit, the output we will receive is this signal. Okay, why it is inverted? Because of this minus sign. Suppose if RC is not 1, some other value, just multiply. Suppose RC is 2 means what happens? It goes up to 4, it goes up to minus 2. Sorry, minus 4, right? Here for your convenience, I have given RC, R and C as these values, such that the product is 1. Suppose you are getting R's and C value, product is 3. What you will get? It will go up to 6 and go negative, say go up to minus 6, right? Right. Now we look at another problem where the input is a square wave. Instead of a triangular wave, we are going to give a square wave, right? What is going to happen when I differentiate dV in by dt? See, this is constant. Differentiation is 0. This part is also constant, 0. So this part is also constant. But where the change is happening? Change is happening only in, change is happening during this part. During this part. During this part. During this part. This is where the change is happening, right? Okay, what is the change? The change is 2 minus 0, but time is only 0. 0 minus 0 in the denominator, right? So 2 by 0 is infinite. That is why I represent this cap symbol. It shows that it is going to infinite. This signal is called impulse signal. This signal is called impulse. Okay, the symbol represented by this cap symbol, right? This is called very important impulse signal. Impulse signal says that it is going to amplitude is infinite. Amplitude is going to infinite. That is why we make this cap symbol, cap. Okay. Now, what about this? It is coming from 2 to 0, right? So 0 minus 2. So it is minus 2, time is 3 minus 3. Denominator, dt is 3 minus 3. Okay, I can make a mark here. What about dt? dt is 3 minus 3. So it is 0. What is the change in amplitude? 0 minus 2. This is your dV. 0 minus 2. So it is minus 2 by 0. So it is minus infinite. Similarly, for this we go to plus infinite. This comes to for the negative edge. This is positive edge goes to plus infinite. Negative edge goes to minus infinite, right? So this is my dV in by dt. But our expression is minus RC into dV in by dt. So RC is 1. So minus means so positive impulse goes to negative impulse. Negative impulse goes to positive impulse. Okay, this is what we will get in the output, right? These are called also impulse signal is also called spike signal. These signals are used in your automobile. If you are going to ignite, you start your engine. Okay, sudden rise in current or sudden rise in voltage may be required. In that case, we can produce this impulse signal. Just give a square wave and you differentiate it, you will get an impulse signal. Okay, now I will give some assignment problems for you. You please work out these problems. Okay, let me say the input is Vn of t is 3 sine omega t. This is 3 sine 50t. Let it be 3 sine 50t. R value is 1 mega ohm. 1 mega ohm. C value is 3 microfarad. Question is find V naught of t. V naught of t as well as sketch the waveform. Sketch V in and V naught. Sketch V in and V naught. Okay, this problem I am giving it as an assignment, right? Okay, the input is 3 sine 50t, R is 1 mega ohm, C is 3 microfarad. You try to find out V naught of t for the given differentiator circuit. This is the expression you have to use. Okay, and sketch V in and V naught of t, right? Practice this problem. Okay, next we will move into practical differentiator. Here, what is the drawback we are facing is when the frequency becomes larger, the gain of the system becomes very large or infinite. For that, what we are going to do is, I have just added a resistor. There we had in a ordinary differentiator, we have a resistor and capacitor. Here we have another resistor. That is the change, right? Now, what we are going to do is, we are going to represent the C in terms of its impedance, right? So for R, the unit is ohm, in impedance is ohms. For C, the unit is farad, in impedance it is 1 by j omega C. For L, the unit is Henry, where in terms of impedance, j omega L. These are the basics. We have made a separate video for this. You watch those videos, right? Okay, so with this, we are going to find out, again we are going to apply Kirchhoff current law at the node A. Incoming current is I1 and I2, outgoing current is I. What is I1? The current flowing through the R1 and C. R1 and C, right? The voltage is V in minus 0, V in minus 0 divided by the total impedance. Total impedance. What is the impedance of R1? R1 is R1. C it is 1 by j omega C. So R1 plus j 1 by j omega C. Voltage by impedance is the current. Similarly, where we have the impedance is, once we are dealing with analog circuits or AC signal, means definitely we will have the impedance, right? For a DC circuit or a constant voltages, we don't have any impedance. We have only the resistive elements, right? Okay, that you have to keep in mind. Similarly, what is I2? The current flowing through R2. So V0 minus 0 by R2 equal to, what about the current? The current flowing into the op-amp is 0. Why it is 0? Op-amp has infinite input impedance, so it is 0. right? Other things are just pause the video, mathematical manipulations, right? We are taking this, we are bringing out this, so we got v naught by v in as this term, right? Fine. Now we look at the magnitude. What is the magnitude? Magnitude of j, this term is this numerator. Magnitude of denominator is omega square c square r1 square plus 1, right? From the denominator we are taking omega c r1 outside, right? So it becomes the square root of 1. Here we get this term in the denominator, right? Fine. Now the important thing, this omega c gets cancelled out, right? So this is what remains. This is the magnitude of the practical differentiator. Okay, now what is our problem is, there in the ordinary differentiator, when the frequency is becoming very high, the gain also becomes very high, right? Now here what I am going to do is, I am going to increase the frequency. I'm going to put the omega as infinite. Omega as infinite, 1 by infinite is 0. So R2 by R1, R2 by R1. So this is the advantage of going for a practical differentiator, right? A ordinary differentiator will have a gain as infinite at high frequency, or very high gain at high frequency. But in practical differentiator, we can limit it to R2 by R1. So we'll go into the magnitude response of the, we go into the first slide. This is how we got the magnitude response. What happens if you look here, when omega is increasing, gain or magnitude response is also increasing. But in a practical, because of practical differentiator, what happens is gain gets constant. So I will use different color. I will use red color. Gain will be limited to, instead of going to infinite, gain will become constant. Sorry, use red color. This value is 20 log R2 by R1. Log R2 by R1, right? So this is the characteristics of or magnitude response of ordinary differentiator. This is the characteristics of practical differentiator. This is the characteristics, right? This red line. This is for practical. Practical differentiator, right? So the order differentiator problem at high frequency is solved by the practical differentiator. Next we will move into integrator circuit. Okay, this is the integrator circuit. The only difference is when compared with the differentiator. In differentiator, we have the capacitor here, we have resistor here. Just we have interchanged the position of R and C. Okay, we will get the integrator. Okay, now other things as usual. This is node A. This is virtual ground. Virtual ground has a potential of 0 volt, and applying Kirchhoff current law at the node A, I1 plus I2 is equal to I. What is I1? The current flowing through the R. So it is V in. The potential here is V in. The potential here is 0. The potential difference is V in minus 0 divided by R. And what about the current flowing through the capacitor is C into differentiation of V naught minus 0 by dt is equal to 0. Right? Other things are simple mathematical manipulations. Just I need output. Output is equal to minus 1 by RC. See, this is already get. Then integrating both sides, we'll get this expression, right? Okay, so output is equal to integration of the input signal. So that's why it is called integrator, right? Okay. Now see, to analyze, for analyzing purpose, what we do, we'll convert things from time domain to frequency domain, right? Already we have seen about some frequency domain. Differentiation means j omega, integration means 1 by j omega. Integration means 1 by j omega, right? Since we have an integration here, I am going to put it as 1 by j omega. From time domain, I am converting everything to frequency domain. So vc of t, so v naught of t convert to v in of omega. Oh god, see, I made a mistake here. Yeah, I have to change this to everything is just I have to in place of in I have put out. I just okay. Now I will change everything. So this is v naught of omega. This is v in of omega. This is v naught. This is v in. So v in v naught. Okay. Now, yeah. If you look at this. This is the time domain expression. I have converted into frequency domain. Instead of integration, I have just to put 1 by j omega. And I have changed v naught of t to v naught of omega. V in of tau or v in, this is because of integration, I changed it to tau, right? V in of t to v in of omega. Now, that's 1 by j omega. 1 by j omega is taking complex conjugate, multiplying numerator denominator with j by j square. My minus is that j square is minus 1. So 1 minus 1 by j, I can write it as j. Okay. Now what is the output by input is j by omega RC. Fine. So this is the gain, output by input in frequency domain. Okay. Now I'm going to find the magnitude response. In magnitude response, what we do, we'll take the magnitude, right? What is the magnitude of J1? Magnitude of denominator term is square root of omega square r square c square. Square root square and square root and square get cancelled out. So 1 by omega rc. Expressing things in decibel scale. So 20 log magnitude is equal to 20 log 1 by omega rc. So this is the magnitude response. What about the phase response? Phase response, if you look at this expression, just a moment, yeah, fine. Look at this, d naught by v in of omega. For j, the phase angle is 90 degree. So the phase angle of v naught of omega is, see here also I have to change, it should be like, here it is v naught. V naught, here it is v in. Okay. So we will subtract, right? If you divide, angle gets subtracted. If it is multiplied, angle gets added, right? So v naught of omega, this angle is in denominator, so minus v in of omega. For j, the phase angle is 90 degree. 90 degree. Okay. And for omega rc is a constant, the phase angle is 0 degree. Okay. Now we will plot the magnitude response. For that, this is the magnitude 20 log, the magnitude is 20 log 1 by omega rc. Observe that what is going to happen is, I am assuming that R and C value as 1 mega ohm and 1 microfarad, so the product is 1. So 20 log 1 by omega, because R and C becomes 1, product of R and C becomes 1, right? So if you put omega as 10 power minus 5, so 20 log 1 by 10 power minus 5, that is, you use a calculator, 20 log 1 by 10 power minus 5, I can write as 20 log 10 power 5, that is equal to 100. Similarly, if I put omega as 10 power minus 4, I get 80. Okay, so we can see that the magnitude, when the frequency increases, the gain gets reduced. Fine, gain gets reduced. What is the issue with this, right? The issue is at low frequency. At low frequency, gain becomes infinite. Low frequency means DC, constant, right? Gain at omega equal to 0, gain becomes infinite, right? And because C is open circuit, circuit becomes open loop circuit, right? You look at this example, or you look at the circuit, you can understand. Okay, the capacitor is here, right? Capacitor is here. We know for a DC input, okay, or a constant input is DC, means what happens? Capacitor is open circuit. When capacitor is open circuit, the op amp becomes, there is the capacitor is open means op amp becomes an open loop op amp. There is no connection between output and input. So for an open loop op-amp, gain is infinite. Okay, that is what I have mentioned here. At low frequency, gain becomes infinite because C is open circuit and circuit becomes open loop circuit. Okay, it should be not C is open circuit. Okay, you can open circuited. Okay, this is the concept, right? So the problem with the integrator is at low frequency the gain becomes infinite. So we have to overcome this problem. Okay, how to overcome this problem? We'll see that. Before seeing that, we will work out a problem, simple problem. So this is the expression for the integration. Integrator, simple integrator. R and C, R value is 1 mega ohm, C is 1 microfarad. Okay, this is the input value. We are going to integrate. What is integration? Is nothing but finding the area. Okay, so what is the area of this rectangle, positive rectangle? It is amplitude is 3, height is 3, width is 2, so 6. So at time 2 it is 6. Okay, similarly here here it is minus 3, here it is 4 minus 2, the time width is 2. Okay, so it is minus 6. So from plus 6 it is reduced, from plus 6 I am going to do minus 6, so it comes to 0. Okay, this is what we get when you integrate the input signal. So integration of this waveform, integration of square waveform gives the ramp waveform. Okay, but the expression is minus 1 by RC integral of input signal. So it is minus 1 by RC means what happens? RC is 1. So just a minus remains. So what happens? Instead of positive triangle, I will get a negative triangle. Right. Now I ask you to work out a problem, practice problem. Let me say the input is 4 cos 50t. 4 cos 50t. R value is 1 mega ohm. C value is 4 microfarad. Sketch V naught of t and V in of t. This problem you work it out. Okay, you sketch the, for you can just Google how to sketch the cosine waveform of 50t. You learn, you work out this problem. Fine. Now we will see the how to solve the problem of the integrator by going through the practical integrator. So this is the practical integrator. In the practical integrator, the difference is when comparing there in an ordinary integrator we have only R and C. Here I added a new resistance R2. Okay, other things are the same. And remember that for solving this problem, we have to find the impedance of this entire thing. Okay, then only you can easily find out what is I2. What is I2 is the current flowing through this R2 and parallel with C. Okay, so R2 parallel with C. And you know that for an impedance, we already see that C is represented by 1 by j omega C. Okay, instead of j omega, I am going to replace with S. Okay, this constant is S. In Laplace transform, we will use this. So instead of impedance of the capacitor, I represent is 1 by j omega C. Instead of that, I will put 1 by SC. S is nothing but j omega. So this R2 and 1 by SC are parallel. Okay, so when they are parallel, I can multiply those impedances divided by the sum of those impedances, right? So finally, this together R2 parallel with 1 by SC I represent by Z. So Z is equal to, I get this R2 by SR2C plus 1. So the current flowing through this Z is I2. Okay, that's what we have seen here. The current flowing through this entire thing, the dotted dead dots, okay, is I2. Now I am going to apply Kirchhoff current law. I mentioned Kirchhoff voltage law. Kirchhoff current law. At node A, the current is incoming current is I1, this current is I2, the current entering into the minus terminal or the inverting terminal is I. And we know the current entering inverting terminal is 0 because op amp has infinite input impedance. Okay, what about I1? I1 is nothing but the potential difference is V in minus 0 by R1. V in minus 0 by R1. What about I2? I2 is the current flowing through the Z. What is Z? Z is nothing but the impedance. What is the impedance? Where the impedance is coming from? Impedance is coming from the resistor R2 and the capacitor C. Capacitor C impedance is 1 by SC or 1 by j omega C, because S is j omega. For convenience, what instead of having j omega, I am replacing j omega with S. So I have found out Z already. So Z is there. So V naught, this potential minus 0 by Z. Okay, so V naught by V in is equal to minus Z by R1. Now you substitute Z value. What is Z? You substitute the Z value, you get this expression. I think some mathematical manipulations. R2 by R1 I get, right? Okay. Now we'll find out a solution for the problem of the ordinary integrator. What is the problem? I am replacing S now with j omega. Now, if I put omega 0 means what is the meaning? That is at DC input. Input is DC. Okay, input is DC. This becomes 0. 0 plus 1 is 1. So minus R2 by R1. So this is the gain at DC input. Okay, that for DC input in the ordinary integrator we will have an infinite output, but here we have only the finite. We have overcome the problem of the ordinary integrator by going for the practical integrator. In practical integrator, only change I have made is only by just I connected a resistor R2. Okay, now what is going to happen? We are going to change the response. If you look here, I will change the color, use red color. So at low frequency, this is at low frequency, the gain becomes this is the gain. Okay, this is R2 by R1. Okay, R2 by R1. This red line is the characteristics of practical integrator. This green line is the characteristics of an ordinary integrator. Okay. Now we look at some applications, right? If you look at this characteristics, it's very clear that when frequency is increasing, gain gets reduced, right? So what I can say, integrator is a low pass circuit. At low frequency, gain is high. So signal moves from the input to the output. At high frequency, signal gets reduced. So integrator is a low pass circuit. Similarly, if you look at the characteristics of this is the characteristics of the magnitude response of the differentiator. What happens? At low frequency, the gain is less. At high frequencies, gain is large. So this differentiator circuits permits high frequency signal and blocks the low frequency signal. So it is a high pass filter. Okay, so differentiator is a high pass filter. Integrator is a low pass filter. Okay, it permits only the high frequency signal and that is blocking the low frequency. So that is why I say it is a high pass. Differentiator is a high pass, integrator is a low pass. Okay, other things like this, like I can say that if you look at this waveform, if you look at the, just a moment, yeah, yes, okay, these things, see, this signal waveform changing and all will use in so many applications, right? For example, this is your television screen. The cathode ray television we had before in our home will have a screen. How this it will be working is, the every time the pixels will be scanned from the left to right and immediately will come to the left. Okay, it will be like this. It will be scanned. Then that's why we will see them. It's like it scans very fast, such that we will see the movie is running. Right. This is how our TV is working. The previous TV, cathode ray, the huge large TV we had in our home. Okay. Look at what is this waveform. It is going suddenly decreasing. Nothing but the sawtooth waveform going suddenly decreasing. Going suddenly. How this waveform is generated? This waveform is generated from like this waveform. If you I can say if you integrate this, we get this, right? if you need a waveform like this, what I have to do? The input should be, I can make it right like here. The input is here. Okay, if I give an input waveform like this, the output will be, right? This is the input, this is the output. Like this, we can use this signal is used for TV scan. Is for few examples I have given to you, right? So it has some wide application, right? Based on the signal requirement, we can convert a square wave to triangular wave. Just you have to control the width and amplitude of the waveform. Thereby, we will get a sawtooth waveform or a short triangle waveform signal of our interest, right? So for wave shaping applications, the major application is wave shaping. Wave shaping application, we are using this integrator and differentiator. I said earlier that impulse signal which we obtain from differentiating, this is the input, means this is the input. If I differentiate this, differentiate B in, what I will get? The impulse. Okay, during positive impulse, negative impulse, positive impulse, negative falling edge, negative impulse. These are used in automobile ignition. Okay, and as I mentioned earlier, your differentiator is a high pass filter. High pass filter, that is, it will it blocks low frequency, permits high frequency. Similarly, integrator is a low pass filter. That is, it blocks high frequency, permits low frequency. Okay, so if you conclude, what are the applications? A few applications is wave shaping application, and I said that this is used in automobile ignition, and differentiator is a high pass filter, integrator is a low pass filter. Okay, um, thanks for listening. I hope you learned something useful from this video. We will come up with some other interesting lectures in the next video. Do subscribe the channel. Any doubts or clarification, please ask in the comment section. Jai Hind.